Welcome everybody. So today I'm going to talk to you about some things related to Lewis structures for covalent compounds. One of them, or ions, is called coordinate covalent bonds. So with coordinate covalent bonds, the idea is that you have a covalent bond, but both of those electrons that are in a given bond come from the same atom. So some classic examples of this, and I'll just define this here. This is where both electrons come from one atom. And what I mean by this is, take for example something like NH3. And so when I have NH3 in water there's H plus ions that are floating around. Well, these H plus ions, these are basically a proton. They don't have any electrons, so these have no electrons. So these H plus ions can bond and are attracted very highly to those lone pair of electrons on the nitrogen. And you'll form a coordinate covalent bond where both of those electrons came from the nitrogen. So this forms what's known as, and you might know this, ammonium, which has a +1 charge. We see this also if we have water and we put in excess acid. So water has these two lone pairs. When we add an H plus, again, we'll get the same thing where we have one of those lone pairs forming a bond with hydrogen, and now this is called hydronium. But we can also see coordinate covalent bonds where they're not as clearly shown. You know, for example, like I could have a situation where I have SO2. And SO2, if I draw it out with dots here, we have a double bond, and we have a single bond. And if I start assigning electrons, like where are these electrons coming from? Which oxygen is giving which electrons? If I do that with, a different color, like let's say purple. Well, this oxygen right here, if we zoom in, this oxygen has 1, 2, 3, 4, 5, 6. And this oxygen over here has 1, 2, 3, 4, 5, 6. The sulfur, therefore, when we focus in on this bond right here, it becomes apparent that that sulfur has given 2 electrons to that bond. That bond is a coordinate covalent bond. So this just gives you kind of an idea of how coordinate covalent bonds work. All right, so let's talk about something related to Lewis structures, one of the skills you need to know how to do, and that is resonance structures. So what happens if you can draw more than one Lewis structure? And so we'll look at something called resonance structures. That's the first consideration that we need to think about. And so with resonance structures, all that I'm doing is I am moving the electrons. And so, like we have a situation where we have SO2. So SO2 I can draw it like this, where I have all my dots. But what's to stop the oxygen on the left from having a double bond? The answer is nothing. In fact, these electrons right here, they can move out. And a pair of electrons from here, any of these pairs, I'll pick this one, they can move into a bond like this. And what we'll get is we'll get a resonance structure where we have a double bond and a single bond. So here we have resonance structures. Well, which one's correct? You might think, well, the one on the left, I like that one, or the one on the right, I like that one. And it turns out that neither are really correct. They're both correct. So we have what's known as equivalent resonance structures. And so what ends up happening is you have to think of this in terms of neither of these structures actually existing. This kind of being like, a human convention. Humans trying to make sense of resonance. When we look at these structures using things like X-ray crystallography, where you can tell how long the bonds are, what we see is that the two bonds, the bond on the left and the right, they're equal. You don't have a double, you don't have a single. You kind of have a resonating structure between the two. And a lot of times they'll draw the resonance structure like this, where they draw the singles, and then they draw the dots like this, and then what they do is they draw like a dotted line, and we could do that in like red here. So they draw a dotted line. And what that red dotted line shows, that shows that the electrons are mobile. The electrons are delocalized. Now the thing is that not all resonance structures are like this. Some resonance structures are not equivalent. I take, for example, this resonance structure where we have carbon dioxide, which everybody draws like this. But you could draw this where you have a triple bond, or you could draw this where you have a triple bond on the O on the left. All of these are resonance structures, but they're not equivalent. And in fact, the best resonance structure out of them is this one right here, the C double bonded O. Now, why is that the case? Why is this the preferred resonance structure? It has to do with something called formal charges. Formal charges are basically fake charges that are assigned to each element as if the electrons are shared equally. Now, when we think about electronegativity and the pull of electrons by each of these atoms, they're not sharing equally. Yet, formal charge says, well, what if they were sharing equally? And if they were sharing equally, we would want two things to emerge. We would want the formal charges to be close to zero. That's first. And then secondly, what we would want is, we would want the more electronegative, if necessary, more electronegative element to be assigned the negative formal charge. So what is formal charge in terms of, like what is it actually equal to? Well, let's see. It's equal to the number of valence electrons minus the lone electrons, not pairs, lone electrons, so you count the dots, plus number of bonds. So when I look at CO2 in the middle here, and I go and I put CO2 like this, and then I put all the dots, if I assign all the formal charges, what I'll see for this, if I change the color, the formal charge for oxygen, it has 6 valence electrons minus 4 lone electrons plus 2 bonds, so its formal charge is 0. Carbon has 4 valence electrons minus 4 bonds, so its formal charge is 0. And this oxygen is the same as the one on the left. Its formal charge is 0. This is why the structure is considered to be better. If we tie this into something called, to the coordinate covalent bonds that we saw before, if we look at our oxygen with a triple bond, it would look like this. If we were to draw in the dots, what we see happening is as follows. With a triple bond, if we draw the oxygen in red, the oxygen's electrons would be 1, 2, 3, 4, 5, 6. When we have a triple bond here, it's showing that this is a coordinate covalent bond between carbon and oxygen. That means that carbon somehow is pulling those electrons, those 2 electrons from oxygen towards it. And we know based on electronegativity that that isn't the case. And when we look at the formal charges, the oxygen would be +1 in this case, carbon 0, and this -1. So using the formal charge rules, we can see that the oxygen isn't going to be +1. Okay, so here's another example formal charge here. What I'd like you to do is, for a side assignment here, is pick the best resonance structure and tell me why. They did the formal charges for you, which was nice, so you can tell me why, which one is the best. This structure here is just showing you ozone, O3, and notice what they're showing here is they're showing that these 2 bond lengths are the same. And what that means is that those bonds are equivalent. Ozone you could draw like this, with the 2 resonance structures. In reality, because they're equivalent resonance structures, what you end up with is you end up with an O like this. And the electrons I draw here, and I'll highlight them, they are able to move throughout delocalized electrons. All right, in the next 2 minutes, I just want to touch on the exceptions to the octet rule. So something important, there are three elements that have less than an octet. So we have the electron deficient, and that would include hydrogen. That would include beryllium, which can form 2 bonds stably, and boron, which can form 3 bonds. Now, boron can form 4 bonds, and we can see that down here with this example that I'm circling in purple at the bottom of the screen. But with this example here, if we assign the formal charges, what we'll see is that the structure that's more important on the left here has all formal charges of 0. If you assign the formal charges here, this F would be +1, and this boron would be -1. That wouldn't make any sense, because basically if we were to look at coordinate covalent bonds, we'd see that F is giving up its electrons to boron, and that doesn't happen. F is so electronegative that the chances of it actually giving a double bond are pretty much 0. And so these structures, they don't really exist, only this first structure. So boron will form 3 bonds. We also see this, or you'll see this later when we talk about hybridization. Beryllium, you could do the same thing. We could have a beryllium that bonds like this, or we could draw beryllium like this. So this one I want you to do. Assign the formal charges to each one. Don't forget to put in all the dots here. And tell me which one is the best one here and why, in terms of formal charge. Hydrogen can never form more than 1 bond. It just doesn't have the room to do so. Now what about going over? Now we talked in class a little bit about having d orbitals for those elements in period 3 or above. And so we see this, silicon, phosphorus, and so on. These elements will violate the octet rule, they'll go above. Now, something like this we saw with XeO3, we didn't actually do this one, but you could draw XeO3 like this, and then put in all the dots around it. I'm using lines to save time. But when we compare it to this structure here, and you assign the formal charges, you'll see oxygen 0, 0, -1, and xenon is +1. 1, 2, 3, 4, 5, 6, 7, yep. When we assign the formal charges here, we have -1 for each oxygen, and then xenon being +3. So that just doesn't happen. So it turns out that when we look at compounds and we say, well, are they going to violate the octet rule or not, we have to consider their formal charges. If their formal charges are better, then they will end up being favored. Go back and do SO4. So pause the video and do SO4 right now. And remember I said it looks like this. Compare SO4 to -2 SO4 with single bonds. Do the formal charges for these two and see what you get. Now, here are some other examples where we violate the octet rule. Remember, step 8, the last step of the Lewis structure, said, draw the Lewis structure. If you have extra electrons, add them to the central atom, violate the octet rule. We see that with ICl4-. ICl4- has 36 electrons total. If we just draw ICl- like this with the 4 Cl's, and then we put the dots around, we would be at 32 electrons. We need 4 more. So where do we add the 4 more? Well, we add it to the iodine, the central atom. Now we're going to tie this into the shapes, because the shapes will also show us this. Here's XeF2, one other example. So XeF2, that one has 22 electrons. If we give each one an octet, we're at 20, and so then we need to add an extra 2, so we can put any of these on, and then we'll have 22. So in that lab, you'll see there's lots of practice, so we'll keep doing those. We'll go over this in class and clean up any questions that you have. Thanks for watching.